So I'm going to talk about the Einstein constraints and the construction of solutions that have a certain localization property at infinity. So in the beginning, I will basically review some work and some earlier results. And then I will present essentially 3 results. There is one result where I will tell you how we can parametrize all solutions in a neighborhood of some given solution, basically. And there are not many parametrizations that you can find for the constraints. And I think this is really an issue that needs more attention to explore somehow the space of solutions. So here's the setup will be to describe all solutions in the neighborhood of a given solution, basically. Then the second result will be about the localization in cone-like domains, proving subharmonic estimates. And then the third result will be to establish super-harmonic control on the construction. And this will be the main result for this lecture. Everything I will present today is a joint work with Bruno Le Floch in Paris. He's my son, and we have been working on that for a couple of years. And before this result, I was also working with The-Cang Nguyen, and so I will also mention his name for some of the results. So this first screen will show you the notations that we'll be using. So you can see the constraints, and I have some kind of standard notations for that. Maybe the only thing I need to emphasize is that the curl H will denote the Hamiltonian operator. Curl M will be the momentum operator. And when I put them together, I just, not surprisingly, I just use the letter curl G to denote that. Okay. So the constraints consist of a second order equation for the metric. I mean, everything is coupled, obviously, and a first order equation for the extrinsic curvature. Now, it's convenient to introduce this H by removing the trace of K from K, as written on the screen. And that's the equations we would like to study, and we would like to construct a class of solutions and parametrize solutions, as I mentioned. Okay, I need to switch to the next screen. As many of you would know, there is a very large and rich literature with 2 main techniques, the conformal method and the variational method. I put some of the names on the screen, but many people have been working on this, on constructing solutions to the constraints, leading to major achievements about the existence of initial data, some explicit constructions, physically relevant solutions, etc., with connection, obviously, with general relativity, but also, of course, with Riemannian geometry. So the talk will be on a specific class of solutions that are Euclidean, asymptotically Euclidean. And the way that people have constructed classes of solutions is typically by gluing. You give me 2 solutions, I cut each of them, and I try to glue them together across some intermediate regions. And Carlotto and Schoen have worked on that using the second method, the variational method, and this would be my emphasis for this lecture today. And I would like to refer, if you don't know this review, to the review by Alessandro Carlotto, this living reviews in Relativity, which is a fantastic and a very extended paper. So there are many names of people working in this direction. Now, in this vast subject, I'm concentrating on the problem of constructing asymptotically Euclidean initial data sets, and more precisely looking at the phenomena of anti-gravity or shielding discovered by Carlotto and Schoen, then later on extended by Cruciel and Delay. And the philosophy is that you would like to localize your solution to decide that in certain angular directions, your solution is prescribed to be the Euclidian metric or to be the Schwarzschild metric. And in some intermediate region to connect these angular domains, you would like to find a gluing, to find some way to glue them together. So obviously the positive mass theorem is implying some restrictions about what you can put at infinity. And part of my work is devoted to understand to make some advances in this direction. What was discovered by Carlotto and Schoen is that you can do that by constructing a solution that is identically Euclidean, except in a narrow cone. That's basically the typical shielding property where everything would be flat, except in a narrow asymptotic cone going to infinity. There are some other developments in this direction by Aretakis, Makroniensky, on characteristic gluing, so a completely new problem compared to the kind of gluing that people were doing before. And there is also a result by Mao Tao in domains that are slightly smaller than cones at infinity. So in that situation, my work is concerned with some sharp estimates for the solutions at infinity. Carlotto and Schoen, in their construction, were able to do the gluing by establishing estimates that are sub-harmonic, which intuitively is not the best behavior you would expect, because Schwarzschild would be a 1 over R, or I'm thinking in dimension 3, say. In dimension 3, you would have 1 over R for Schwarzschild, and if you glue it to Minkowski at infinity, you would expect to have also a behavior of the order of 1 over R. And this is basically what we are going to prove. And Carlotto and Schoen were able to get subcritical control on the gluing. But they were conjecturing that gluing should be possible at the harmonic level. And this is what I've proven in these two papers. So there was a method we call C2 solution method some years ago with The-Cang Nguyen that gives a partial answer to this question. And more recently with Bruno Le Floch, we have a complete answer of the question that was raised by Alessandro, Carlotto, and Schoen. So this is what I would like to show today. Before I really enter the subject, the details of the new result, I'm showing you an old result. So the philosophy that I have here is that I assume that some kind of ansatz is provided, which I call a seed data. So a seed data for me is a metric G1 and the second fundamental form H1 that are prescribed, and they are prescribed with a certain decay at infinity. But the decay is not supposed to be fast. It's just slightly faster than 1 over square root of R in dimension 3. And in the same time, I'm assuming that when I plug these ansatz in the two operators, these operators have more decay. So I introduce another parameter, PM, that measure how good is the decay at infinity in terms of evaluating the operators. So this is my assumptions. And then I can prove that based on this sort of ansatz, there exists a solution to the vacuum Einstein equations. And in addition to that, we were able to analyze the decay of these solutions. But the decay of the solution depends on the ansatz in the following way. If M stands for matter and capital G stands for geometry. So I have geometric exponents and matter exponents, if you like. So if my this PM is less than 1, I have an agreement that will be, if you like, similar to what Carlotto were proving that is slightly less than harmonic. And if I want to obtain a result that is harmonic in terms of decay, of control on the solution, there is something new that is happening here, is that there is a term that I will explain more later that appears in this expansion at infinity, this m tilde over r. And if I build my ansatz, which is easy by some kind of expansion at infinity, so building this seed data is not a problem. The difficulty is to go from the seed data to the actual solution and then to control its decay. So these are the issues I'm talking about here. So in this first paper with Nguyen, in the case where the ansatz is built so that the matter exponent Pm is greater than 1, then there is a result which is super-harmonic in the way that it is stated. So there are some additional terms, this m tilde on which we have a certain control. Now, the problem that was posed by Carlotto and Schoen can be stated in the following way, and that was solved to some extent by them. You look at infinity, asymptotic infinity for asymptotically Euclidian solutions, and you split it in 3 angular regions. There is an angular region, and I have a picture right below, I think. So this is like a cut of the picture. So this is supposed to represent 2 cones that are a small cone located inside a big cone. So this is what I'm describing on the top of the screen. CA is a cone of a certain angle. You have to think of it as being possibly very small. Then there is a complement of the same cone, but slightly larger angle. So there is a gap in between, which I call T. There is a T transition region. And what Carlotto did was to prescribe inside the small cone the metric to be Schwarzschild, for instance, and outside the big cone, the metric to be Euclidean. And then they solved in the intermediate region, which they call the gluing region. Okay, and so the question raised by Carlotto in this setup is whether we can construct solutions that have this 1 over r harmonic decay in all angular directions. So the result I had proven with the CAN already, in fact, provided an answer to this question. So you see the pictures that I put here, where there's a big Euclidean region, possibly small angular region with Schwarzschild, and 1 over RP, strictly less than 1 region. So this is the pictures that Carlotto had. And the picture that I had 3 years ago was this one, where now I built a solution that is going to be asymptotically Euclidean instead of being exactly Euclidean, but it will be asymptotic Euclidean with a very high rate. So maybe I just show you the statement which is below. So we still have these 3 regions. There is a region where instead of Euclidean, it's asymptotically Euclidean, but at a high order. So you see this Q exponent strictly between 1 and 2. You see the region where Carlotto wanted the solution to be Schwarzschild, that for me, it's asymptotically Schwarzschild with a high rate of decay. And then there is the intermediate region where the decay 1 over r is achieved. Okay. So of course, this was not the exact answer to the question posed by Carlotto and Schoen, but from a certain point of view, I found it physically natural and as the exact localization problem. So I call it the asymptotic localization problem. And in fact, the exponent Q could be taken as large as you want, okay, by refining our arguments. I may return to that later on in the end of the talk, but I may not have time for doing that. Okay, so this was what I was doing before. And what I would like to show you now are basically 3 results: how you can parametrize the solutions, localize initial data sets near a given one, and then how you can solve it at the harmonic, you can solve the equation at the harmonic and super-harmonic level. So first of all, I'm going to have a couple of definitions to pose a problem, where I will begin by telling you what I mean by a reference. So localized reference set will be a manifold, a metric, two tensor, and a weight that helps me to localize a solution. There's a gluing domain, like before. You can really think of the examples that I just show you, except that my framework is not restricted to this example, but keep in mind the example of the two cones. So omega will be the domain between two cones. And what we would like to do, we'd like to take this weight to be positive inside the gluing domain, to vanish at the boundary, to vanish at the asymptotic ends, if there is any. But again, is the example of the cone, that would be the case, that there will be one end and this weight is going to zero. And I found it convenient to take the weight to be plus infinity in the complement. And I can even give you a little bit more structure about that, how this weight is built by looking at the distance. So this weight will be 1 over r, where r is a certain distance that I can compute at asymptotic ends. And there is also a factor b, which is a distance to the boundary of my gluing domain. Okay, so it's quite intuitive. I have something that will serve as a reference. There is a domain of gluing and a weight that is adapted to it. Now we are going to work in weighted Hölder spaces based on these weights, omega and b, like I'm defining it here. So we have weighted Hölder, Lebesgue, Sobolev spaces. And in fact, some of the norms you will see later on in the statements will be triple norms. I put 3 bar to denote the Hölder norm, to which I'm adding the L2 norm of the function itself without derivative. So it turns out to be good for our estimate. So what we do with that? So we have a reference set. So we know where, roughly speaking, our solutions will live. And what I'm going to do is I'm going to parametrize the neighborhood of this set and then project it to get an actual solution. So the parametrization is done by introducing decay and accuracy exponents. So I call them PG, PQ, PG, QG, PM, QM. So the matter exponents are bigger than the geometric exponent. And what I'm going to call a localized C data set is a G1, H1, H star, M star, where G1 is a Riemannian metric, H1 is a symmetric two tensor, as we expect. And these things will be small in Hölder norm with a weight omega, according to some parameters epsilon g. And in addition, I'm looking at how these quantities act on the operators. And I also measure the size of these operators in the same Hölder norm, except that you should notice that I'm using now the triple norm to state that, but it's essentially the same. Everything is scaled in a good way, that since, for instance, this H is a second order operator, I found it convenient to call it PM plus 2 for the decay exponent. And curl M is a first order operator, so I'm writing QM plus 1. So the notation have been, adjusted. So in principle, everything is very easy to follow. So what we are doing now is to seek for a kind of projection from a seed data G1, H1. I would like to produce a solution, to project it in some sense on the solution manifold. So I'm following what Corvino and Schoen had proposed based on some kind of energy computed, determined by the dual of the linearized Einstein constraints. And in the end of the day, what it means is that the metric, or the deformation of the matrix, is G minus G1, can be expressed as a certain weight times the dual of at G1H1 of the Hamiltonian, or the dual of the momentum linearized at J1H1, and evaluated at some point. UZs that are computed as minimizers, so they are given by a fourth order system, PDEs, basically. Okay, so this is how a solution are characterized. They are actually characterized, even though the equations initially were second order and first order. This characterization, this way to pick up the solution, is fourth order and second order. So there is a fixed point Picard scheme that has been proposed by Corvino and Schoen, and basically that's a tool that we use to proceed with this projection. So to give you a little bit more insight about that, what I'm doing now is that I'm writing the operators that we solve. So the operators are the linearization of the constraints with some weights combined with the dual form. So what it is a sort of bi-Laplacian with weights for the first component, and the second component is more involved somehow geometrically, because a U is a scalar, but the Z is a vector. So that's, anyway, this is a structure, and I think I wrote below the actual operators that you have to solve to look at asymptotically Euclidean ends, and this is what we do. So basically, our work consists of looking at fundamental solutions for these operators in a situation where you have these weights that are degenerate and select certain asymptotic ends and certain conical domains. Like I'm going to be more precise about that, but you already see, you know, the nature of the result and techniques that we have developed. Okay, so what is the solution mapping for us? So we have a reference set. We give some pairs to evaluate the decay and the accuracy of our C data. And now, in addition, to define the solution mapping, we need two more exponents, which are called P and Q, which we are using now in the following way. So we can prove that to any seed data, localized seed data set, we can associate an exact solution of the Einstein constraints, which is given through this map. We call it localized C2 solution map. And the way it works is that we can find U and Z, so a scalar field and a vector field, so that G1 can be modified. So this is where we see, I make that more precise in the next screen, but some kind of projection is happening. You start with G1H1 and you build G and H by finding U and Z, so that this correction, you know, in the image of the dual linearized equations will produce an actual solution. So in addition, we want to have a control. At this stage, it's just a definition, but soon there will be a theorem saying that there exists such a map. And so the map is supposed to be in these Lebesgue-Hölder norms to be controlled. So I want to have a nice control of the metric by basically by the data. So G is close to G1 in the Hölder space, and U and Z are also close to that. Okay, so at this stage it's a definition, and I want to think of it as a projection in the following way. I'm going to define an equivalence relation between two pairs of tensors, G1H1 and GH, by saying that they are in the same class of equivalence if you can find U and Z so that they are connected. You know, so the G, the difference, G minus G1 is a certain weight times the image of DH star or DM star. Okay, so this is really the way that locally near the reference we get a parametrization. And sometimes, I mean, in this subject, people are more interested in looking at one specific construction, so they somehow miss the formulation in the way that we put it here by having quantitative estimates for the solutions and precise assumption on the decay exponents, as you will see next. Okay, so by definition, we can send the map, localized C2 solution parametrization is this map that send J1, H1 in the neighborhood of the reference set to an actual solution in the class, in the same class. Okay, now to use that, you have to make a specific choice of the reference. And for us, in the rest of the talk, it will be asymptotically Euclidean. You need, having done that, you need also to maybe first actually to specify the gluing, sorry, it's really part of the reference that goes together with a gluing region. So having this setup of the reference and the gluing region and the weight, you have to establish weighted Poincaré, weighted cone inequalities, I mean, to check the coercivity of the first order operators. And to do that, this is a place where the geometry of the gluing domain will come in the picture, okay? And the decay and the accuracy exponents, there will be conditions on that, okay? So this is a part that I think we made very clear with our results, and this is what I'm going to show now. Okay, but so far it's a list of definitions. I think it's a setup that is nicer, more clear than what had been done in a similar direction before. But use it. You have to be more concrete about how this G0 H0 is chosen. So this is what we will do. And having done that, we'll be able to check the coercivity and invertibility of this operator in, as I already said, in weighted Sobolev, Hölder-Sobolev spaces. Okay, so behind that there are results about the structure of the linearized Einstein equation at this fourth order in this presentation. And typically to see the ellipticity, you have to go back to an old or very old paper by Douglas and Nierenberg in this subject. Okay, so I'm moving to basically the second result is to now apply this parametrization in a given situation of cone-like domains. So what I'm describing on the screen is a little bit more general than the cone. I mean, it's definitely more general. So we have these assumptions that our localized reference is asymptotically Euclidean. At each asymptotic end, you can define the radius that I had defined before. You can make it to coincide with the radial distance. Okay. The radial distance in these coordinates. And so I have that reference, it's asymptotically Euclidean, and then I need to fix a bit of the notation about how this radial distance is defined. So I take it to coincide with radial distance in the coordinates at each asymptotic ends. And then the gluing domain needs to be specified. Okay, so roughly speaking, it's a cone, but not necessarily defined by the difference of two cones. the way we define it here is to fix some angular weight on essentially on the sphere at infinity. I mean, it's defined as a whole manifold, but so it's a function that is smooth, it's positive in the support, and the point is that asymptotically it is scale invariant. So it really represents at least for large lambda, or it could be an asymptotic condition that we impose. Okay, so let's say maybe it's exactly cone-like at infinity, and we can also arrange a distance to the cone that I call b before to be the same as this function chi. Okay, so it's just a bit more setup and more geometric restrictions that what I had explained before. And now to proceed, I first want to understand how I can achieve gluing with a control that would be sub-harmonic, like Carlotto and Schoen had done before in a slightly more restrictive geometric situation and without looking at the whole parametrization. Okay, so to do that, I just remind you that we have basically two limits. So one comes from the ADM mass, or so it's in dimension 3, it will be 1/2 as a decay, 1/square root of the distance. And again, in dimension 3, it will be 1/r for the harmonic decay. Okay, so this is this interval that will come about in the exponents that I'm writing now. So I'm going to say that my geometric weights, PG and QG, that we had to describe the decay of the metric, I'm assuming that they satisfy this inequality. So one side, the first inequality has to do with the ADM mass, except that for us, it's quite convenient to include the case of equality. So it may, I mean, you choose this PG the way you want, right? This is some ansatz that you decide at infinity. So if you like the ADM mass to be finite, that's fine. But we found it interesting to include this lower bound in our theorem. And the upper bound can be understood easily by going back to the the form of the equation. So basically, you should think of the metric to satisfy the sort of Laplace equation, this quadratic source, in terms of, I mean, this is obvious by just going back to the basic equation. Okay, and so this is a reason why we have the second inequality. Now, the second inequality implies a lower bound for QG, bigger or equal to n/2, and this is the same. This is just the limiting case for the ADM momentum to be defined. Okay, so again, you want a strict inequality, you can do that, but for us, it's more natural to also include that. Now, there will be sub-harmonic conditions, like I wrote on the screen, harmonic conditions, super-harmonic conditions, and basically the three regimes will correspond to three different results, except that I'm only showing you sub-harmonic and super-harmonic results. But depending on the exponents, you will get different results. Okay, now you remember that there was some PQ in describing the decay of this map. So I'm going to say that this PQ is effective for my given seed data, which has certain exponent satisfying this same condition. If PQ is sub-harmonic, that's the first thing I'm going to be able to prove. And PQ cannot be bigger than these matter exponents. Okay, so you build some ansatz, and then you do kind of projection and hope to construct a solution. So you do get a solution, but how good is this solution controlled depends on how good the ansatz was. Okay, and this is exactly what this inequality PQ less than PMQM is telling you. So it's completely natural, expected. And then there is another condition, Q minus P minus 1 less than PG minus 1. And I would like you to only think of that in a case where Q is equal to P plus 1, which I call it balance case. And it's a kind of typical case you may assume. Okay, so this is our the second result I want to show you, and the first existence result with Bruno Le Floch. So we are given a cone-like asymptotically Euclidean reference set. We consider exponents where PG, QG is tame the way I define it. PQ is called effective, so in particular, it has to be sub-harmonic. And then we can now prove that everything I somehow announced before, that there was a seed to solution map that you could define and generate an exact solution. So this is indeed true. I have this map. And to prove that, you need to prove Poincaré, as I mentioned before, cone estimate, Poincaré estimate with weight. The weight should be consistent with my assumptions on my different exponents, etc. Okay, so this is it. And if you look below, you see what I mean by the balance regime, where the Q exponents are simply taken to be the P exponent plus 1. So if you do that for all three of them, you see that this result holds under very natural conditions where, you know, I mean, I can just repeat myself, but everything here is making clear all the constraints, the very natural constraints that you would have expected and are written up here. Okay, now what we want to do, and this is a main result for this lecture, is can we say something more, right? Can we take this PQ bigger? So the way we proceed here is to, in fact, pick up the C2 solution map, which depends on P and Q. So it's a projection. You have to be very careful that some of these things depend on the way the projection is done. Maybe not a very strong way, but they do depend. So we found it convenient to take P and Q to be actually the lowest values, right? Which will be 1/2 and say 3/2 in dimension 3. And look now at strongly tame, strongly effective decay. So that's a new definition that I would like to make. So basically, I'm going to make stronger assumptions, which I call strongly tame and strongly effective. And strongly tame is defined by asking simply that the matter exponents are at least these harmonic rates. Okay, so again, I'm always thinking dimension 3. So PM would be 1, and QM would be 2. So these are the conditions that you have to impose. I mean, otherwise there's just no hope to, to get a good the estimate at the super-harmonic level. So you need to do that, and it just means that you have to construct your ansatz a little bit more carefully by adding terms in the ansatz, if you like. And there is an integrability condition that is not too surprising if you think about it. And so I want to emphasize that what I'm talking about here are a sub-harmonic control, but still I'm talking about solutions that have a very low decay, right? So I'm only talking about some kind of error terms that I want to control in my estimates, but it doesn't prevent the metric to be very bad in terms of decay. So the first condition here allows very low decay, and even like 1/√of R in dimension 3. But the last two conditions have to do with the accuracy of the seed data. This is what I just explained. Okay, so strongly effective will be conditioned on the exponents. So I called them PQ before, but now it's convenient to give them a different name and put a star. So P star, Q star are more or less the same exponents I was talking about before. So I'm going to say that my exponents are strongly effective is the exponents where I want to measure my solutions will now be stronger. So they will be harmonic between n-2 and n-1 for P star. They cannot be too big for the same reason. So there's some limitation in terms of behavior of the geometric exponents and the matter exponents. And you also have some extra conditions that mixed up P and Q, which I could also explain. So if you look below in the balance regime, it really again means a very natural condition for P star. So this P star, I want it to be more than harmonic, and it cannot be bigger than, say, the next harmonic exponent. And it's also controlled by the geometric exponent, but more importantly by the matter exponent. So this PM could be very large, but it doesn't mean that I'm going to immediately control the solution at a higher order. Okay, so having these definitions, I can now give you the last ingredient. And the ingredient comes from a kernel at infinity, basically, as you could guess. So we study the fundamental solutions of the fourth order operator, which is behind this analysis in the gluing domain, and we built a finite collection for each asymptotic end, for each connected component of the support of our angular weight. We built fundamental solutions, basically, and more precisely, we give a name to the main terms that describe the decay at infinity of U and Z, and this is given, as you can see on the screen. So U will be 1 over x to the power n minus 2 times now a certain coefficient. I wrote below what happens if you have no localization. So if there is no localization, the behavior will be 1 over r, and then there will be a multiple of 1 over r that pops up. But now, since there is a localization, all these things are localized in a way that I can study, and I can check the shape of these functions. But these functions now do depend on the sphere at infinity. They are non-trivial functions on the sphere at infinity. So this is what I state in this proposition. And finally, the results that we obtain. Okay, sorry, I need some more terminology, which is that. So if you have understood these kernel terms, so nu of the angular variable over r n minus 2, so this term pops up in the expression of the metric as a sort of perturbation of the metric with this presentation. So I'm going to call a modulated seed data set a seed data set, G1H1, to which I'm adding the effect of this kernel written in this way. So there is a mass term for each parameter, small a, and there is also a momentum term also for each of these small a, and the expressions are given in terms of these fundamental solutions that I have studied and constructed by previous proposition. So this is something at this stage, it's just called modulation of the seed data. So it's a seed data to which I'm adding certain effects that are, a little bit involved in terms of the Asian and Laplace operator for the first line, and then you have the Lie derivative at this expression z. So again, the psi a or the new a, they depends on each end, and they depends on the weight, and they are non-constant on the sphere at infinity. Okay, so the theorem that you can now guess is the following. If you give me a cone-like asymptotically Euclidean reference set where I want to parametrize, I understand how to parametrize my solutions, I parametrize a solution with certain exponents, and I evaluate now my solution with other exponents I call P star, Q star. And under the inequalities I mentioned before, I'm able to indeed establish super-harmonic estimates. So the statement is now that if I have some seed data and I construct an exact solution, the exact solution is not going to agree 100% with the seed data, and this is natural. There is an additional kernel term, which I have introduced in my definition of modulated seed data. And importantly, I have all kinds of quantitative estimates with weights, where the weights are assumed. You have optimal inequalities on that. And so the G1 tilde and the H1 tilde involve certain terms that maybe I can show you over here. So what I call M tilde A and P tilde A actually are going, so they modify my seed data, and they are close to quantities that I can evaluate in the first place by looking at the matter terms, if you like, or even if there is no matter, if H star would be 0, M star would be 0, what I do is that evaluate what the seed data, what it gives when I plug the seed data in the Hamiltonian and momentum operator, and then I compute these quantities, MA star, PA star, right? So this is like some guess of what should be the modification at infinity. And below, we prove that this difference is evaluated in terms of the accuracy of the seed data somehow. Okay, and you have Hölder norms to measure that, and also L2. So L2 stands for these triple norms that I was talking about before. So these are the estimates for the corrections. And if I go back to the screen before, we can prove that the G minus G tilde 1 has the decay that you expect with a weight omega, with a localization. So this is really a full answer to the problem that was posed by Alessandro Carlotto and Schoen some time ago. So we have that localized with this angle, and we have also error terms. I mean, upper bound, if you like, this E and F, which are given by also the accuracy of your seed data. Okay, so somehow if you start close, close from the solution manifold, you will get exact solution that is very close. I mean, everything is somehow quantitatively computed by that. Okay, I would like to finish. I hope this was okay. I have an example here. I mean, I cannot, there are a lot of things I cannot show you here about the Corn inequalities, etc., where we have to, to reprove some of these things. But more importantly, the estimate for the fundamental solutions are what we do here. So I'm just showing you again the operators and the explicit solutions here. So to summarize, I would like to say that we have built a parametrization, and again, I think the philosophy which is behind this parametrization should be extended, and we have in mind that everything is small around this given solution, but I think we can do better than that. We focused on asymptotically Euclidian ends, but I really would like now to look at more general asymptotic ends. And I could show you this super-harmonic is control, where the work was to do this analysis of the decay. Maybe a point that I did not emphasize enough is that to do that, you have to be careful about the nonlinearities of the Einstein constraints, beyond what Carlotto and Schoen needed for their estimates. So there are a lot of questions I want to do, and especially to construct more solutions. So all these techniques of gluing, there's a lot of different techniques of gluing. I mentioned some of recent names, some recent work by Corvino, Carlotto, and many people, I think maybe Dan Lee, I think, has done some work. So these are things that personally I would like to learn, to know more, and to possibly extend with the way we have here to look at these problems. And maybe do I have a few more minutes, Pascal? Yeah.
Yes, you have like 5 minutes more. Yeah.
Okay. So I have maybe one or two more slides that I can show you.
Of course.
But before I do that, I have, actually my motivation, most of my work is more about the evolution, the evolution for the Einstein equations. So looking at the constraints for me was like a side problem. I was curious of what was possible to input in a global evolution problem. Okay, but now that I understand better what is possible in terms of constructing asymptotically flat localized data, I would like now to return to what I have done about the global evolution and see what can be done, maybe more specifically about the evolution of these data. Okay, let me, to finish, go back to this page. So I guess I showed you that before. And I think I can tell you more, a little bit about how we prove that, right? So our first result was somehow not localized. I showed you in the beginning 2 results, and this was the second one. And so the very first one was a result with Nguyen, where there was no localization, and we just were saying that we get a control of super-harmonic terms in our result, our theorem. And then I stated this second result, where you see that you get Schwarzschild, Euclidian, 1/r decay. So how do we prove that from the previous result? And the way we do that is that any seed data set is generating a solution, okay, and under certain decay conditions. And this solution has been studied before very carefully in a localized domain. That's the main result I show you. But even if it is not localized, you can do something like I state on the screen. And the way you do that is to play with the seed data, and you change the seed data. You give me some seed data, I compute the exact solution. Maybe I'm not happy with this solution, then I go back to the seed data and you change it, and then I get a new exact solution. And so by some kind of implicit function theorem, and this is what I'm showing you here, I'm actually able to engineer my solution somehow, to some extent. Okay, so maybe without entering the details, I don't think we have time. You can see here, I have a G1 H1 that in this case will be a combination of Schwarzschild, Euclidian, whatever you have. And on top of that, I'm adding some kind of modulation, some other kind of modulation in my seed data. And then I compute the effect that it has on the exact solution. And by a fixed point argument, I can determine the parameters that I plug. So I call it phi, psi, st. So these are parameters. I can play with them to modify my seed data. It's still a seed data. It's still producing a solution. But sometimes I can adjust the parameters to get somehow better properties I want on my solution. And this is exactly the philosophy to get that. And if now I apply this philosophy to the previous theorem, where there were already a localization, what I can do is I can further somehow localize my solution. And this is basically something I would like to investigate in the coming weeks. Okay, I should basically certainly stop here, and I thank you very much for inviting me to talk in this seminar.
Thanks, Professor. That was a really wonderful talk. Yeah, so now we'll take questions now. So if anybody has any questions from the audience, feel free to go ahead and ask.
Okay, so could you just point to the paper again? I think it was pointed out in the first slide, but I think I missed it.
Can you repeat that, please?
Yeah, can you just point back to the paper on which this is based? Because I'd like to give it a read again.
To read again. Do you mean the main result? No?
Yeah, yeah, the main result, yeah.
Oh, okay.
Yeah,
so
this one, yeah.
Here it is.
Okay. Can you point to the paper as well? Okay, good. Okay. Can you point to the paper? Maybe an archive version or so.
I'm sorry, the sound is not too good. Okay, so, can you repeat? I'm sorry, your question, please.
Okay, I'll just put it in the chat. 1 second.
Okay. So we have like two parts. I mean, there is we say there are some kind of modulation to the seed data, and then we actually estimate these additional terms. And this term can also, of course, be related to the ADM mass. So we have some other discussion about computing the mass of this GH or G1H1, etc. With a limitation that there are cases where they may not be finite, actually, but still we can say, I think, some interesting things about the relation with the ADM mass and momentum, energy momentum.
Okay, thank you.
Yes, thank you.
Yeah, I think Professor, he's asking for a link to this theorem, like he's asking for the paper, like that.
Oh, I see. So sorry, I didn't understand that.
Actually, that helped as well. So.
Yeah, I'm going to send it to you. We see if you like. We post it next week, I think, or may take a week or two. But yeah.
Oh, okay. Okay, thank you.
It will be on archive, yeah. So.
Yeah.
Yeah. Do you have more questions, like, from the audience? Okay, if not,
okay,
I guess.
Also, is there?
Okay.
Yeah, just one last question, if that's okay. Yeah. Okay. So, is there maybe a review for this as well? Because I'm actually interested, but I'm still trying to grasp some of the things. So, if there's maybe a review paper that encapsulates some of these, or maybe some references that would help you out.
Yeah, I'm sorry. The sound is really, I don't know, maybe that my computer or something, but I really have a hard time to understand. I'm very sorry.
Okay, I'll put it in the chat because I just got these new headphones and I think that's
yeah. Okay. If you write it in the chat, yeah. I will read it. Oh, I see. Yeah, I mean, you can look at a review of Carlotto that I mentioned. So there is a chapter actually where he was talking about my result with CAN, for instance, before with Nguyen. So there is a section in his review. I think this is the best place to start. I think. And otherwise,
okay.
yeah.
So the living reviews one.
Yeah, it's called
you mean the living reviews paper?
Yeah, exactly. The living review. I mean, it's a fantastic paper. It's 100-something page. It's really, and it's very well written. Actually, I like his style. A lot of details and hundreds of references.
Oh, okay. Yeah, that would definitely help. Okay. Thank you.
Okay. Okay. And otherwise, I send you. I mean, send me an email, and I will not forget to send you the paper.
Okay. Okay. Thank you.
Thank you.
Yeah. Do you have any more questions from the audience? I guess if not, then I guess I'll go ahead and ask, like, 1 or 2 questions to Professor LeFloch. Yeah. So, hi, Professor. Hi.
Hello.
Yeah. So, in like, last time you talked, a couple of years ago, I think. So, so, so basically, the difference between this talk and that talk is like, you improve, like, the decay in this talk is like a little lower. I can't forget, like, is it the improvement of the decay or something?
And now the improvement, Puskar, is about the localization. I mean, this is the hard part here.
Right.
Okay,
Right.
the localization. Yeah, it makes really the life more difficult. If this is what I try to stress that in the talk, to localize is I mean, yeah, give you all sort of technical issues with yeah, it's hard to describe in a minute, but
Right. So yeah. Okay. So this is like, this is completely new. Like,
definitely, yeah,
yeah.
definitely. And this was a question posed by Carlotto and Schoen, right? So they didn't cover that in their paper. Yeah. But I think I like also, I think I like also the parametrization, the way we put it here. I think even though technically there's not really much new things technically for this part for sub-harmonic estimates, but still the way we present it with the parametrization, this was not understood before. If you look at the papers, you often see a lot of different gluing, and people keep somehow repeating similar arguments for different setup of gluing, and it's not always clear what are the assumptions of decay, etc. that are
Right.
relevant.
Right. Yeah.
Mm.
Yeah. Yeah. So also you mentioned the, you have this, the source, like the matter source in the
Right.
equation. It's like,
Mhm.
so it works for like any matter source satisfying that condition, like, this QM, PM, those exponent. Like,
Uh,
do you have any restriction on the matter source, or like it's like,
no. What to say? No, every time we control the Hamiltonian minus this H star. So
right,
it's not a restriction on the matter itself, right?
right,
It's just what we measure is how So it's just a yeah. So it's not a smallness condition on the matter at all, right?
right. So is
It's just
so is the difference between like satisfying the actual equation, right?
yeah,
Okay,
right, right,
right. And
right, right.
yeah, so last question, like, can you, if you have this seed data which is like close to the actual solution, is there like, kind of a evolutionary technique, like if you given that data on an initial hypersurface, can you like evolve this under the Einstein evolution and still keep this smallness?
Um,
Like, what I'm
I mean,
asking is there like, have you like, applied this to like some studying a stability problem or something like that, or like in a dynamical setting? I mean, because yes,
right.
it
So
must
in
be
terms of evolution, yeah, I don't know how much of that structure would be preserved by the evolution. This is what I want to, yeah, I would like to look at. But
yeah, this is very interesting. Like
yeah.
constructing, C solution like this. Yeah. And
Yeah. So I don't think I can say too much now, but the connection at this moment, the connection with this work I did on the evolution is that we also assume very low decay conditions on the metric, right?
right.
And we coupled with matter. So my work with Yuma, that that maybe I just mentioned at the end maybe of this screen is about evolution close to Minkowski space-time, evolution of massive matter. And when we do that, we have rather low decay conditions of the metric. So the metric can decay almost like 1/square root of R. And in addition, we put the matter. So yeah, so this is really a domain of application. But when I was doing this evolution, I was not thinking of localization.
Right.
Okay,
Right.
so basically, you want to add the idea that your initial data are localized, and yeah. So this needs to be done.
Wow. Yeah, that's very interesting. Yeah, really interesting talk. So I guess if we don't have any questions, so I guess I'll just stop the recording.